So it's a real pleasure to be able to share with you some insights on something magical called Kemeny's constant. So, who has ever heard of Kemeny's constant? Oh, that's my PhD student. I'm glad you raised your hand. You heard it, maybe for the title. Okay. So in fact, I will start with an introduction about myself. So I'm working at the EEMCS faculty, Electrical Engineering, Mathematics and Computer Science, the Department of Quantum and Computer Engineering. And one of the sections in this specific department is Network Architecture and Services. So that's basically where I'm located. So indeed, I'm researching networks. And one of the things we do, as was already mentioned, is that we try to quantify the robustness of networks, and we do that by using network metrics, like the degree or the betweenness, stuff like that. So we try to capture the robustness of a network by studying the properties, the graph theoretical properties of the network. So that's basically what we do. And just a little marketing here. So this is a nice overview paper of the graph vulnerability and robustness from 2 years ago. We don't know any of these people. I should also say that. So it appeared in one of the IEEE journals. They have 151 references, including 7 papers from our section, which is, I think, nice. Like 5% of all papers are in the references. So it really means that we sort of have a name in the field of robustness of complex networks. So that's nice. So what I want to do today is to introduce maybe more or less a new constant. Well, only 2 of you have heard of it before. So for most of you, it will be a new metric. It's called Kemeny's constant, and I will show you what it is, and also some research results that we obtained for this metric. But first, where does the name come from? Kemeny's constant is named after John George Kemeny. I think he's an interesting guy. First of all, he was born in Hungary. So in fact, he was not born as John or George, but as Janos Georgi. And you can see when he was born. And what really impressed me a lot is that he was invited to join the Manhattan Project. Who knows what Manhattan Project is? Oh, that's good, right? So, okay, we want to build an atomic bomb, and they invite all kind of clever people, right? Okay, Feynman was there, Niels Bohr was there, but they also invited this 18-year-old, and I think he was still even in the middle school. Unbelievable. Apart from that, he was also the inventor of the basic programming language. I think if you run your Excel, I think there's still Visual Basic somewhere. I don't think anyone is using it anymore, but at least he's also the founding father of one of the first programming languages. So impressive guy. So what is the constant actually? Well, to understand that, I have to set the stage a little bit. Try to keep it simple. So I'm looking at undirected graphs. So basically I have nodes, I have links, and I'm considering random walks. So what do I mean? Let's say I'm in node 1, and then I have 3 options for my next step in my random walk, and I just assume that the distribution is uniform. So basically, every node that I can reach from node 1, 3, 4, and 5, I assume that the probability of going to one of the neighbors is 1/3. Because I have 3 neighbors. So that's a random walk. And then you also can define something called the mean first passage time. So for instance, M13, that's the mean first passage time. I start in 1. And what is the average time it takes to reach my destination 2 on average? Yeah? So that's not so very difficult, of course, to compute. You can write down this series. Of course, there's a probability of 1/3 to reach it in 1 step. So that's the contribution 1 times 1/3. If you don't reach it in the first step, you have to go back, and then you have another probability of 1/3. So you get a series like this, and it's basic calculus to show that this equals. Anybody wants to take a guess? Anyone for bonus points? No? What's the feeling? It's 5. That's cute, right? Yeah, how would you know? I mean, okay. Just a feeling. So now what is Kemeny's constant? If I would take any point, for instance, 1, it is the mean first passage time from a given node. So for instance, 1. to a randomly chosen other node. But here randomly is not really uniformly random, but random in another sense that I will explain later. Yeah. So this constant says something about mean first passage time from one place to another place. Yeah. So it says something about how easy it is to travel over this network, right? So if the value would be very large, right? Wait, Lisa. If the value would be very large, that probably means that the network is not very robust, right? Because you have to spend a long time getting from one place to the other place. But if it's low, it seems that the network is very much connected, right? So we have a lot of redundancy. So we tend to think it's a robust network. Okay, some applications. In fact, I'm only showing one, I think. So during COVID, there was, of course, many publications about many models to say something about COVID. One paper I found in 2020 in PLOS ONE is that they used Kemeny's constant to determine optimal positions in the network where to test for COVID. And you see two colors here in the figure. You see the ones that are magenta, more or less purple. Here you use degree. So these are nodes with a very high degree. So it seems like a good idea, right? If I test somebody with a high degree, because he has a lot of neighbors, seems to make sense. These black dots over here are based on what I call Kemeny centrality. So it's a metric you can compute, assuming that you remove this node. Then you look in the difference in the value of the Kemeny constant. And if you do this, you find these nodes that are really connecting communities, which of course is probably a much better way to do your testing, because then this is sort of gives only a local view, and this gives a more global view. Yeah? So this is a simple application of the constant. Some background. I did this work together with my colleague Johan Dubbeldam, who's from our same faculty, but in Dion. So he's an applied mathematician. Do you have applied mathematicians joining these sessions also? Yeah? Okay, he gave it talk. Great. And part of the work was also done with a former postdoc at Humboldt University in Berlin, Maria. She now left academics. She's now making big bucks in the industry. Okay, that's the choice. So before I start to go into the detail, let's talk a little bit about terminology, what I'm talking about. As I said, keep it simple. We have a graph, undirected, unweighted. I put the nodes there. I have links. And for instance, I would be interested in the adjacency matrix, right? You all know what it is. I always use a capital N to denote the number of nodes, by the way, so it'll come back, and L as the number of links. So this is a simple representation of my graph, the adjacency matrix. I can also discuss the diagonal degree matrix. So that's just a matrix that only has values on the diagonal, and they correspond to the degrees. So for instance, in the middle, here we have this 3, which corresponds to the degree 3 of node 3. And then I can start to have a slightly more complicated matrices, like the transition probability matrix, defined by this formula. And this basically gives the transition probabilities going from one node to the other node. So let's say I'm in node 4, then I look at the 4th row, then I see a transition probability of 1/2 to node 3, and also 1/2 to node 5, right? So it's simple stuff. And then finally, I can also define the steady state, more or less, of this Markov chain, right? Because we're talking about Markov chains in a sense. And that's the left eigenvalue of this transition probability matrix. And it gives you the steady state vector of the random walk. So what does it actually mean? It means that if you would simulate the random walk for a very long time, then these are the fractions of time that you spend in this specific node, right? So you spend 30% of your time in node 3, for instance. Yeah? What else do we need? Laplacian matrix, for just another way of representing your graph by a matrix. You simply subtract the adjacency matrix from the diagonal degree matrix. So you get something like this in this example. So the -1s now denote connection, and on the diagonal you have the degrees. I hope you've all seen it before. We know that there are, of course, capital N eigenvalues for this Laplacian matrix. The smallest one is always 0. Why? Well, you simply put the all ones vector on the right-hand side, and you get 0 if you do the multiplication. And it's the smallest one, and then we go all the way here. This is the largest Laplacian eigenvalue. So this is just the way that this is the notation we use for our eigenvalues of the Laplacian matrix. Then, because this matrix has a zero eigenvalue, we cannot invert it, but we can use a generalization of matrix inversion called Moore-Penrose pseudo inversion. So we denote it by Q dagger. And this is one of the formulas you can use to compute it. Yeah. So it's the pseudo inverse of the Laplacian. And finally, I'm going to explain yet another metric called the effective graph resistance, denoted by R sub J. And how is this defined? Let's consider a graph over here. And now assume that every link corresponds to an electrical connection with a resistance of 1. And then basically, if I input let's say 1 voltage here and I take it out here, then the effective resistance between these two nodes is simply the effective resistance. So you use Kirchhoff law and stuff like that to determine the effective resistance. So it's sort of a generalized distance metric. Some people also call it electrical distance. And then if you compute all of them and you sum them, you get this effective graph resistance metric. And it's also considered in literature as a useful robustness metric. That's why we study it. So one of the reasons why we like it more than shortest path is that if you compute the effective resistance between 2 points, you consider all paths between the 2 points, right? So normally if you take only the shortest path, you leave out all the other information in the network. So this metric contains more information than shortest paths. That's why we like to use it. And now the elegant thing is that this effective graph resistance can be expressed either in Laplacian eigenvalues, like this. So it's the sum of 1 over the eigenvalues multiplied with n. Of course, I leave out mu n because it's 0, right? So I just have n minus 1 eigenvalues. But we can also use it, express it using the trace of the pseudo inverse. Yeah. So I defined on the previous slide this pseudo inverse of the Laplacian. If you have it, you just take the diagonal elements, you sum it, and you multiply it, and you also have this effective graph resistance. So there's 2 different ways to compute it. Okay, are we almost there? Almost there. So there's different ways of actually computing this Kemeny constant. So I gave it more or less a definition in the beginning that it's sort of an average value of the mean first passage times, and that's reflected in this formula. So mji here, in fact, is the mean first passage time from j to I. Doesn't matter what j is. You see, I'm summing over I, but j is the j. That's a free choice that I have. And the randomness, as I explained to you, it's not complete uniform randomness, but it's random in the sense that you choose, let's say, the steady state probability of being in a specific node to weight the average value. Yeah? The fact that you subtract -1 is a technical detail that I don't want to go into here. So this is sort of the original definition. Yeah? But you can also compute it using eigenvalues of this matrix. So you take this diagonal matrix to the power of -1 over 2 times A times the same one. And then you look at the eigenvalues. Yeah. And then you simply take a look at this ratio and you sum it over all eigenvalues not equal to 1. Because the first eigenvalue, k is 1, is 1. It's sort of corresponding with 0 as an eigenvalue in the Laplacian. Yeah. I tried to find how they call this a matrix in literature. I didn't find it. So there's many variations of Laplacian matrices, like signless Laplacian, the normalized weighted Laplacian. I didn't find a name for it, but okay. And then finally, and this is a really nice result, and this is in fact due by Johan Dubbeldam, our colleague, and my former PhD student, Shang-Rong Wang, and also Piet van Mieghem, who's the leader of the section NAS that I belong to. And they found an expression for the Kemeny constants, which basically is a function of this pseudo inverse. So it has this pseudo inverse. It also has the degree factor d. That's easy to get. Again, L is the number of links. And this zeta factor over here is basically the diagonal elements of the pseudo-inverse. Yeah? So in order to compute this, you first determine this pseudo-inverse, takes order n to the power 3. And you also take more or less the diagonal elements, and then you evaluate this expression, and then you also have Kemeny constant. So this is the main topic of their paper from 2017. So basically, there are different ways to compute it, right? So what I'm going to do next is give you a few examples of graph families, where we're giving the value of this Kemeny constant.
It's not equivalent.
What's that?
The three equations, they are equivalent.
They're equivalent, yeah. So they all give the same result, luckily. But in some cases, it's better to use this one, and in some cases, it's easier to use this one. Depends a little bit on the structure. This is a whole list, but some of these items only have 1 or 2 slides. So let's start with a simple example. I'm looking at complete bipartite graphs, right? So I have S1 nodes on the left-hand side and S2 on the right-hand side, and they're all connected with each other, but not within the separate sets. So I denote this with K sub N1, N2. And just by using random walks and probabilities, when you get something like the series I showed earlier in this first example I gave, it's not difficult to prove that you get the sum of the nodes in the 2 sets. So N1 was N2, and you have to subtract 3 over 2. That is just a formula. Interestingly enough, it was not known in literature. Not many people actually did research on this constant until recently. Then we also looked at path graphs. You get this elegant expression, quadratic function of the number of nodes. We played a little bit, still a tree, of course, but we made the diameter a bit smaller. We get this expression. Now it also contains a fraction. And we can even generalize that one by having, let's say, the dependent nodes at a distance m of the end of this part, and then you get this function of n and m. Yeah? So these are just sort of exercises in calculus. Then another class of graphs that we looked at are so-called windmill graphs. They were introduced by Estrada 2016. And how do you make them? Well, you take cliques, you take eta cliques, so a certain number of cliques, and all cliques are order k. And then you connect them by a central node. So for instance, in this case, eta is 2. That's why this 2 is here. I have 2 different cliques, and the cliques are of order 3, and I connect them with a node in the middle. Yeah? And this is W3, 4. I have 3 cliques, and the order of the cliques is 4. I connect them with a node in the middle. Yeah? You might think, well, why did he define these graphs in the first place? Well, he used it because for this family of graphs, you can show that if you blow up the graphs, if you make the size go to infinity, then the clustering coefficient of these graphs goes to 1. That's sort of a local value for clustering. While the transitivity index, which is sort of a global value of the clustering, goes to 0. So normally people tend to believe that these things are always behaving the same, but for this class of graphs, that's not the case. So that's why he came up with it. And then I made a generalization of the concept of the windmill graph. So I call this windmill graph, the generalized windmill graph. I denote it by a capital W prime. So instead of putting one central node, I put a clique in the middle. So I don't have one central node. I have a clique of L nodes central that are connected to all the cliques outside. And one of the reasons why I study that is that I'm working together with a guy here at Civil Engineering who's studying public transport networks. This is an example. This is the metro network in Marseille. And what they do, they represent every single line also as a clique. They call it the representation in p-space, which means that you get a subgraph here, which is blue, which means that you can reach all these points without interchanging, because they all belong to the same line. And the same, of course, holds for this line, the red line. I also get the clique. But the stations where you can interchange, of course, form the core. So this is, in fact, of course, it's not completely following my definition, because the number of nodes here is not the same as the number of nodes here. But this very much looks like this generalized windmill graph. So it's nice that they also occur in papers, in applications. And this is actually work that's being conducted by Odette Katz, who is a professor in transport systems in civil engineering. So that's nice. Okay, so how did I compute Kemeny's constant for this family? Now I use the spectrum of this graph. Okay, well, of course it's a very specific structure, so I can find A and I can find delta. And okay, after some tedious work, I can write down the spectrum. I can write down the eigenvalues of this matrix. So you can see there's this eigenvalue, that's a certain multiplicity. This is an eigenvalue, multiplicity, multiplicity, and also 1 is an eigenvalue. Yeah? And then I simply apply this formula 1 over 1 minus lambda I, and I sum it. And then I get this expression. Okay, well, there's not much to see about this expression, of course, it's just there. And for the special case that I take L equal to 1, so this is the Kemeny constant for the generalized windmill graph, and this is for the special case L equal to 1, so that's the original windmill graph. And you get a nice expression like this. So it's sort of interesting, even though this metric is quite complicated, as you can see from the formulas, it's a very neat expression if you have a lot of structure in the graph that you consider, in this case, the windmill graph. Now I'm going to look at the relation between Kemeny's constant and effective graph resistance. Yeah? But there's a result from Palacios, 2010, and he showed that for regular graphs on n nodes, R regular graphs, so that means you have a regular graph where every node has the same degree, namely R, that this equation holds. So then it's a linear combination of the Kemeny constant is basically a factor times the effective graph resistance. A very elegant relationship. And when I saw that, I thought, okay, what I'm going to do is I'm going to try to approximate Kemeny's constant for non-regular graphs, but I take inspiration from this formula. And I'm going to use the average degree, capital D, which is of course 2L over N, it's just the average degree. And also a measure for the heterogeneity of the degree. So that's called heterogeneity index H. And this is like, well, it's like the variance of the degree, right? So DI is the degree, capital D is the average degree, so this is the variation around the average value. And then I simply assume that my approximation looks something like this. Again, I have this RG, right? The effective graph resistance. I multiply with capital D over N, that's the same as this, only not here. Everyone had the degree R, and this is the average degree, but I still divide by N. But I have to add something which takes into account heterogeneity. So obviously, if H is 0, capital D is R, I'm back at this one. So at least for regular graphs, it is working. And then I decided to choose this function that I don't know yet, such that this expression is exact in case of complete bipartite graphs. And you know, of course, the Kemeny constant for complete bipartite graphs, right? N1 plus N2 minus 3 over 2. Yeah, we do. Okay, so how do we do that? So we're first, oh, I just said that, right? We knew that. And then for this family of graphs, it's simple to compute the average degree and also the heterogeneity index, right? It's also easy to compute effective graph resistance because the spectrum is easy to obtain. And with that, I just plug it into my equation, into my approximation. And then I learned that I have to take F for this specific case of this form. Yeah. And then for this specific case, of course, we know that capital N is just the sum of N1 and N2, and L is the product. So basically, I'm assuming that my FNL has this form. Yeah. So again, this is exact if the network is regular, and it's also exact if I'm considering a complete bipartite graph, right? Okay, so this is my approximation. It's nice. I plugged for D, I plugged in 2L over N, right? But I think by now you understand where this formula comes from. Exact for regular graphs, exact for complete bipartite graphs by construction. And to my surprise, also exact for windmill graphs. And that was a nice bonus. I didn't see this one coming. So this is a small table where I consider a number of graphs. This is, of course, the complete bipartite one, all the way down to some windmills and generalized windmill. And here this is brute force computation by any method that I want. And this is the approximation. Now, for instance, you see for the complete bipartite graph, it's exact. It should be by construction. As I mentioned, the windmill graph is also exact. Nice. But for the generalized one, we see it's underestimating the value. And for the other ones, it's overestimating the values. So for the trees, it's also not exact. Well, okay. So one of the conclusions here is that my approximation K star is not an upper bound. And then I went back to this paper by Johan Dubbeldam from 2017. And in fact, they not only give this exact expression for this constant, they also give an upper bound. And there's something nice with this upper bound. Hey, it contains also heterogeneity and capital T, and also this mu1, the largest Laplacian eigenvalue. Remember? So this is an upper bound, a tight upper bound, because in some cases the value is actually achieved. So what I did then, I do the same exercise. I take a number of example graphs, and I also compute this upper bound by using this formula. And what you see here now, it's much tighter than this K star. And also, another bonus here is that for the generalized windmill graphs, it's also exact. Of course, you cannot conclude that from this table, but we were able to prove it also analytically. So that's nice. What we did next, of course, the networks we considered so far are very small, right? We have maybe 10 nodes. Okay, maybe the windmill graphs have like 35 nodes. It's a little bit more, but still not too big. What I always like to do also with my students is to take a look at real world data. And normally we take it from something called Internet Topology Zoo. So these are more than 200 communication networks. For instance, they look like that. So these are real communication networks with nodes and links between them. And we use those as the network, a set of networks that we use to compute how well our approximations are working. This is a list of the 3 smallest and the 3 largest networks in the database. This first one is interesting. It's from 1969, ARPANET 1969. This is in fact the very first internet ever. So the first experiment conducted with the internet was considering this ring topology. Do you know what happened with the first message that was sent over the internet? So they wanted to send the message login, L-O-G-I-N. So L, okay, O, okay, G, okay, then it crashed. So the very first experiment on the internet crashed. That was the topology. Another thing, look here, for instance, the Renam network, 5 nodes, 4 links. Can you make a conclusion on the topology of this network? A tree, yeah, that's true. A tree. Can you find? Do you have more conclusions? Do you remember the formula for the Pn, n squared, blah blah blah? But you maybe also remember complete bipartite graph. A star is also a complete bipartite graph. Remember? Star. 1. And 1 is 1, and 2 is 4. I get 1 plus 4 minus 3 over 2, please. 3 over 5, right? You can do that one of the other forms, and we'll get a different value. So this funny thing is that even this simple table proves that the topology for Renam, and also in fact from Ren, are star graphs. So the largest ones have the order of 754 nodes and a couple of 900 links. You can also see, not too bad, right? Not too bad, but KU, so the upper bound from the pseudo inverse, is really good, very close to the actual values. So this is some statistics taken from all 243 real-world networks. So I think best to look at the average absolute error for my K star. It's 27%, so big high, pretty high. But the upper bound KU, its average error is lower than 1%. So it's really impressive, I think. That's quite good. And we also did it for a slightly larger network. So the largest network in the previous slide was 750 nodes. This has 15,000 nodes. So it starts to be a bit demanding computationally. We can still compute the Kemeny's constant. We have 250,000 edges. And this is the real value of K. This is my approximation K star, and you can see it's way, way, way too big. It's almost 7 times bigger than the actual value. Yeah? And this is the upper bound KU based on the pseudo-inverse, and you can see it's very close to the actual value. That's nice. This is a nice case which shows the strength of this upper bound. Okay, so what we did next is we come up with a class of biregular graphs. So these are graphs where only 1 or 2 degrees are occurring. And how did we build this family? We start with the graph G1, which is K1 regular on N1 nodes. And on the right-hand side, we take another graph, G2, K2 regular with N over 2 nodes, N2 nodes, and we join them. So what does it mean? So here's my G1. I put that, yeah. So here I have 10 nodes. Everyone has three neighbors on this part. Here I have 8 nodes. Everyone has 5 neighbors on this part. And then every node on the left, I connect with all the nodes on the right. Yeah, that's called the join of G1 and G2. And we were able, okay, before I show what we were able to prove, I give 2 specific classes that fall in this biregular family graph that I just explained. So if I start on the left-hand side with N1 nodes without any links, and on the right-hand side I do the same, what do I get? So I start on the left with isolated nodes, and on the right I take isolated nodes. Then I do the join. I'm connecting everything from left to right, and I have a complete bipartite graph. And we already knew here what the result is for the upper bound, right? Then I take for G1 eta copies of a clique of a complete graph of degree m, and I join with 1 node in the middle. What do I get? Windmill. Here it is. So these are my graphs. They form G1, and in the middle I connect them. Yeah. So this one also falls in this class. The thing that we proved is that for this class of biregular graphs that I just explained to you, we can prove that this upper bound is tight. So it gives the actual value of the constant, which is nice. So that means that what we have already seen, that this upper bound is tight for complete bipartite graphs and windmills, is something we can also prove for a larger family. Well, the proof basically exploits the properties of the eigenvectors of Q. So here we're really also working with Q and this pseudo-inverse. So it's quite a tedious proof, a couple of pages, but we managed to pull it off. And this has been submitted, and we're waiting for the review comments. So this is just an example. So here I take 100 nodes. I run my Python script to make a random regular graph on the left-hand side. Same here, I connect them, and I just compute both my Kemeny constant and my upper bound. And in fact, they coincide. Not a surprise, because we have proved the theory. But it's nice to check it anyway, right? What I always try to do. So this result holds for graphs that are biregular with diameter 2, well, a specific family of graphs that have these properties, but it's not sufficient for this upper bound to be tight. So this is a simple example. So what is this graph? This is in fact something called Peterson graph, but it's only Peterson if you do not have this link. So without this link, it's a regular graph. But if you add the link, indeed it's a biregular, right? Because everyone has degree 3. Here. But these have degree 4, so it's biregular, and the diameter is also 2. But still the upper bound is not tight. Yeah? So the upper bound does not correspond to the actual value of Kemeny's constant. Then just a few words about analysis for large networks. I think the largest example I've shown you so far is this example with 15,000 nodes, but we want to go beyond that. Now let's take another close look at this formula. So this is the exact expression in terms of the pseudo-inverse. This is the upper bound. And if you want to compute the pseudo-inverse, it takes you n cubed, the order n cubed. However, on the right-hand side, we only have this zeta vector, which contains the diagonal elements of the pseudo-inverse. So I don't need the whole matrix, only the diagonal. And in fact, and that's why I'm working together with people in Berlin. People in Berlin have been working on approximations of this diagonal. So this is work that's already a couple of years old. And when I started working with them and I learned about this result, hey, that's great. So we can use your approximation, their approximation, to make the computation of this right-hand side fast, right? So I can make a fast approximation of the diagonal elements, which basically is the zeta vector. But there will also be some errors due to some sampling that's taking place. Let's say it's represented by this epsilon parameter. So it is much faster than computing the complete thing, right? But you lose some accuracy, right? That's how it goes. So we try to validate this on a number of, again, real-world graphs. And we basically split them into a group that we call medium size, and they go all the way to 32,000. And we also have large, and they go all the way to 365,000 nodes. And in some cases, the links also run over more than 1 million. The first result I'm showing you is, what do we see over here? This is more or less this sampling value. So 0.1% means, for instance, that 10% of my choices that I make. So I'm not looking at all the possible solutions in my computation, but I'm only considering 90% of the possible solutions. So that's like a sampling metric. And you see that if I increase it, so the more I sample, the larger my error becomes. But at the same time, you can also achieve a very high speed up. So that's the idea of this approximation, of course. So if we use this method, it's possible suddenly to compute this upper bound, or at least approximate it, for very large graphs. So that's in fact what we did. So this is the set of large graphs, and even the largest graphs in here. In over more than 1 hour, we're able to compute an approximation for this upper bound of Kemeny's constant. So with this method, computing the constant really comes in reach for very large networks. So for future work, as I mentioned, we look at the constant as a proxy for network robustness, but we did not really apply it yet to use cases. So we're looking for interesting use cases where we can use our methodology to say something about network robustness, and also translate it to the application domain. One possible application domain, in fact, is detecting anomalies in bank transactions networks. Some of my colleagues in TNO are working on this, also with graph metrics. And for instance, one metric that's quite often used, even by banks, is PageRank. So the PageRank says something about the importance, of course, of a node. And then if there's a new transaction and there's a large change in the PageRank value somewhere, then this might be a red flag that something suspicious is going on. Because this K also takes into account random walks and many paths between different nodes, we think it also might be an interesting metric to try to use for looking for anomalies. Of course, in the banking world, even if you, let's say, increase or you decrease false positives, even with a little like 5 or 2%, it's already very useful. But I think this is an interesting direction. And finally, of course, the Kemeny constant, I started defining it based on random walks. And of course, we also have the concept of quantum random walks. People that are working on quantum are also looking at quantum random walks. So we also have the idea of defining quantum Kemeny's constant. So I don't know yet what it means or what we can do with it. Sounds like fun. These two. So wrap up. I gave some explicit expressions for Kemeny's constant for some graph families. We discussed an approximation using effective graph resistance. Not too good performance, sharp upper bound, very good performance based on the pseudo inverse. We looked at some validation on the real world networks, and I also introduced a new class of graphs for which the upper bound is sharp. And we also take a quick look at the analysis of some real large networks.